Joan. You know, it's a pleasure to actually take a trip where I don't have to go through O'Hare. I go past O'Hare. So, first of all, I want to thank you very much for inviting me to come out and talk with faculty, interact with you about something that's near and dear to my heart. I'm very passionate about this field of assessment. And thank you so much for showing up on what is one of the nicest Friday afternoons we've had in quite a while. I guess it has something to do with the coffee and the goodies. So I'm hoping that what will happen this afternoon is we'll have a dialogue about assessment and ways to think about assessment that make it productive for us as faculty and for our students. And a little disclaimer, this is not about the nuts and bolts of writing items or scoring items or things like that, or psychometrics. That's for another time, okay? It's certainly not for a Friday afternoon. But this is about assessment, and it's about trying to think about what are the most productive ways we think about assessment, or should think about assessment, relative to curriculum and instruction. But just as an opener, since we're talking about assessment, one of the things we always need to remind ourselves when we generate items or questions for our students is to be clear what assumptions we're making about the question. So here's a perfectly reasonable question, right? Find X. Here's an answer. Now, what is this an example of? It's an example of the fact that when we write an item that says find X, what we're really saying is find the value of X. Okay, and it's clear to us what the intent is of the question, and now this enterprising student decided, and you can find lots of these other examples on the web, but one of the things to realize is that assessments are in some ways a form of dialogue. They are an interaction between an instructor and a student, and they have rules of discourse. And this item has certain rules of discourse. And these are things just for us to think about, because one of the things that's inevitably the case is we pose a question to students, and the answers we get back are not always what we expected. So we can explore things like that, but I just thought this was a good reminder when we sort of think about, be careful how you ask questions, given the nature of the answers you're likely to get. So what I want to do this afternoon is sort of work through a set of topics that start with situating assessment in the context, in a larger context, the so-called where, what, and why of assessment, and then deal with two really critical issues that I would hope help us think deeply about assessment. One is from a theoretical perspective, and the other is from a practical perspective in terms of issues of theory and issues of design. And then what I'm going to do to try to illustrate the points I want to make and to set you up for the exercise I have in mind for this afternoon, and so I'm going to make you work a little this afternoon. You're going to have to work for that coffee and the goodies back there. We're going to sort of go through a little exercise that gets started using some of these ideas and stimulates a conversation about essentially assessment, but more so in the context of what do we really want students to know and be able to do in our courses, in our programs. And then if we have time, I'll come around to some issues and things like technology and things like that. We may not get there. That may be for another time. And while I go through this stuff, I want you to ask me questions. I want you to stop me. I want you to ask for clarification, etc. So let's start with the where. It's important for us to recognize that, and this is an issue in the K-12 world, and it's an issue in the post-secondary world. That is, assessment should be part of a coordinated system that involves curriculum and instruction. And the three things together should, in fact, be complements of each other, in the sense that when I think about curriculum, what I mean by curriculum, it is some specification of what it is that we want students to know. It could be something like standards that we use in the K-8 realm, the Common Core State Standards, or the Next Generation Science Standards. It could be a specification of a set of topics or areas we want students to learn in a course or across let's say a set of courses in a major. So it's the stuff or the description of what it is we want students to learn. Instruction, for me, are the things that we do as instructors and the things that we ask students to do that help them learn that stuff. That is the sort of the teaching and learning activities or transactions that involve trying to make whatever is the target of instruction or the curriculum available to the students and have them acquire it. And then assessment is the way in which we monitor whether we're being successful, whether they're being successful. And sometimes, maybe not, this is true in higher ed, but it's also painfully true in the K-8, K-12 world, that teachers spend their time trying to run around the edges of this thing, trying to align things. And in fact, one of the big problems we have in the world of K-12 education is that assessment tends to drive the process. Large-scale, high-stakes assessments of the type we have here in Illinois, we have throughout the country, they tend to skew the process in the sense that they become the de facto curriculum, because what gets tested is then what gets taught, and what gets taught is some version of what was intended to be learned. Okay? And this can also be true in the higher ed context, but it's certainly true in the K-12 world. Now, notice I put at the core of this thing the idea that what should be driving this whole thing and what should be holding it together and making it cohere is that we have some theory, some empirical evidence of what it means to know and learn the particular content that we're interested in. So, and of course, I'll say a little bit more about that, but the point is that the driver of a lot of what we do should be framed in terms of what do we think it means to know something? What's the nature of the process that students go through by which they learn it? And then how do those things help us organize or structure the curriculum, organize the instructional activities, and then determine the assessments that are going to tell us whether we're being successful and whether our students are being successful. So, so whenever I think about assessment, and much of today's conversation about assessment is really going to be trying to relate assessment to two things. Curriculum and instruction, but also to the idea of what are these theories of knowing and learning, as best we can articulate them. And those theories, when I say theories, I mean they can be theories that are based on empirical research, or, and in many cases they're our personal theories. And one of our problems we have is we all have personal theories of learning and knowing. And many times those personal theories are what drives the process. And it's only when we're forced to articulate those personal theories and how they align with other disciplinary perspectives that we come to realize that my theory of knowing is different than your theory of knowing, which in turn gives rise to my exam looks very different from your exam. And we can talk about that, but in terms of the implications. And we'll try to get to a place where we get around that fact of the personal theory. So let's talk about what and why of assessment. Basically, the way to think about assessment, and this is not just educational assessment of any type, is a process of gathering information. We gather information for the purpose of making judgments and making decisions. So we assess the quality of our air. I was just in China recently, and my God, they have a problem over there. The quality of their air is awful. So we assess the quality of our air. We assess the state of the economy. We assess the quality of education. We gather evidence to make judgments as to, are we doing okay? Are we improving? Is it getting worse? And typically, it's because we want to use that information to make some decision. Now, in educational assessment, the information is designed to help a variety of players in the educational system. And I think this is very important to realize, is that assessment is designed to provide information that serves various individuals and various purposes. And so sometimes it's to help instructors, sometimes administrators, sometimes accrediting agencies, sometimes policymakers, and in many cases it's also the public. The public wants to know about the state of education. And so the idea of educational assessment is to infer what students know and how well they know it. And again, presumably the reason for that is by knowing that, we'll be able to enhance future outcomes. If we know something about how well students know something or other. And of course, another very important part of thinking about assessment is that some of these outcomes of assessment are more immediate and some of them are more distal. So we can think about the use of assessment in the context of the classroom to guide instructional decision making. It's sort of moment to moment, day to day, week to week. And the idea of that kind of assessment is to improve learning. The more we know about how our students are doing, the better we can adjust to their needs, and therefore we can change the trajectory of learning. But others are much more delayed, such as the use of assessment for program evaluation. And this has interesting implications because essentially it causes us to recognize that there are a variety of contexts and purposes, and these distinctions make a difference. They make a very big difference when it comes to thinking about the design and use of assessment information. So by context, I mean the fact that the contexts range from small-scale context, what happens in my classroom, what happens in your classroom, to essentially a more intermediate scale, what happens in our department, what happens in our college, to larger scale, which could include a university system, it could include states, nations, it includes international assessment. So assessment occurs in all these different contexts, and the assessments that occur in these different contexts often are designed or intended to serve different purposes. So these are just three of the purposes, but they're the three that is the easiest to distinguish. Oh, and I should have said something. All my slides, Joan has them. She has all the stuff, and you're welcome to use them. And you can email me about any of the stuff or whatever. She has it in PDF form. I'm happy to share PowerPoint slides or whatever. I just realized I should have mentioned that. The three important purposes are what's called formative assessment, to assist learning, summative assessment, which is to measure individual achievement, for example, at the end of a course, at the end of a semester, or to evaluate programs. for accountability purposes. And the problem that this poses is a problem that one size does not fit all. This is a very big problem in the sense that an assessment that is designed to fit one purpose and do it well will not necessarily serve the other purpose well. I think one of the best examples of this is in our current world of K-12 education and policy. We administer tests like the ISAT, which are very broad brush achievement tests. So our kids sit down, they take a 60-minute test in math at the 4th grade level, and that 60-minute test has a certain number of items on it. It samples from the whole area of what 4th grade math is, and the information that you can glean from that assessment can be useful for certain purposes of trying to sort of say, okay, how are 4th graders doing with respect to the curriculum that we wanted them to master? On the other hand, we also make the mistake of telling teachers, oh, you know what? You should be able to use the information, teachers and parents, you should be able to use the information from that state achievement test to make important judgments about what your kids know and don't know. And the answer to that is that's patently false. Okay? That is something that cannot be delivered by those assessments because they can't give you the kind of information that you need to make judgments at a detail enough level to tell you what is it that Jimmy really knows and doesn't know, what are his strengths and weaknesses. So this problem is that we tend to think a test is a test is a test. And this is a problem for educators. It's also a problem for policymakers. Policymakers are saying, well, why can't we just get it all done with one test? Oh, and by the way, don't make it too long. Don't make it cost more than $3 a head. And make sure that we can turn the results around in 3 weeks. Well, you know, you laugh, but that's the policy world, right? It is. And the thing we have to recognize is that educators at different levels of the system need different kinds of information. A teacher needs diagnostic information. A state policymaker needs a very broad brush stroke about what's going on. They have differing priorities, they have different constraints, they have different trade-offs. They have different cycle times. The cycle time for which you're going to use the information is absolutely critical. So teachers need it on shorter cycle times. Policymakers, administrators can take it on long cycle times. Okay? So what this means is that assessment is a more complicated business than we oftentimes think it to be, and we end up with all sorts of tensions in the world of testing and assessment. And it's true to some extent in higher education as well as it is in the K-12 world. Now, one of the things I'm going to mention here, maybe we can come back to it later, is that the literature and the research on assessment has looked at or tried to answer the question of what kind of assessment provides information that has the most impact on improving student learning. And the answer is very, very clear. The answer is assessment that is close to instruction, that essentially that is intended to serve a formative assessment purpose. By formative assessment, what I mean is we assess students, we figure out what it is that they know and they don't know, and we then act upon it in terms of giving them feedback and changing the conditions of instruction. I'll just give you a little taste of that and sort of why it's important for us in the back of our minds, even though this is the hardest thing to do, to focus on the formative functions of assessment. And it's because something we've all experienced as instructors. As we're teaching, we need information to evaluate whether what we're doing is working, and we need information about the current understanding of individual students or groups of students so that we can take the most appropriate steps for instruction. So what are some of the ways we do this in higher ed? How many of you use clickers in your classroom? Ah, there's somebody, okay. How many of you know what clickers are? Okay, you all know what. So why use clickers and what are clickers about? Well, used well, what clickers are for is to present a key question to your students, maybe in the middle of class, around a topic where you know there's a strong likelihood that they have very differing understandings. And the whole point of presenting that question at that moment in time is to allow them to anonymously respond, and you get a distribution of answers which demonstrates to them and to you, oh, 1/3 of the class believes this, 1/3 of the class believes that, 1/3 of the class believes that. Is that the way you use your clicker questions? Okay, now these have to be well-designed questions, and they have to be questions where you have a pretty good idea that, you know what, these students are likely to have a misunderstanding of this important principle in psychology or in chemistry or whatever. What it allows you to do now is to have a discussion as to why students might be believing that and correct the misconception right then and there. Okay? Now this is hard to do. It's hard to do because one, you need really good questions, and two, you need a mechanism. But what formative assessment allows you to do is to provide feedback to students. Turns out, we've known this for a long time. I'm a psychologist. The psychology of learning tells us something, which is you can't learn without feedback. Okay? You need feedback to learn, and one of the problems we have typically with assessments we do, that the feedback cycle is either very weak or it's non-existent. Okay? How long does it take for us to give students back their papers? How much time do students actually have in which they get feedback? So feedback is needed for students to monitor their learning. Paul Black was a physicist, and Dylan William, who's a mathematician, reviewed the impact of formative assessment practices on learning outcomes. That is, they looked at studies where instructors had implemented this practice of formative assessment. Now, formative assessment is not a thing. It's a practice. It's a practice that's enabled by having good exercises that give information that makes it possible for you to act on it and the students. And what they reviewed was the fact that formative assessment is probably about the most powerful educational intervention we have ever found. Okay? It produces effect sizes ranging from 0.5 to 0.7. And from those of you who don't know what an effect size is, essentially effect size is measured in terms of the degree of difference between two treatments relative to the variance. So 0.5 means that it produces a half a standard deviation gain in achievement. And one of the questions was, a lot of this stuff comes from the K-12 world. Does it work in higher education? Well, if you look at, and I'm just going to quickly cover this, and maybe we can come back to this as a discussion of this later. There's a variety of studies that have been done in higher education that have looked at providing feedback to students based on tests and quizzes. And a student who used to work with me at Vanderbilt, Jeff Nyquist, categorized all of these studies in terms of what kind of feedback was provided to students, ranging from the weakest condition, which is just knowledge of results. Knowledge of results means you just tell the student they're right or they're wrong. Okay? To essentially feedback conditions where you're telling them knowledge of results, but also knowledge of what's the correct answer plus explanation, and then what he called moderate formative assessment. That is, knowledge of results plus the correct answer plus essentially specific actions that you could take to essentially clarify your mistake or your misunderstanding, to a much stronger one where there's some specific activity. And when he categorized studies, this is what he found. And again, this is a while ago, but it illustrates the point that even in higher education, where oftentimes we're talking about quizzes and other things like this, that if we just give students right-wrong feedback or even minimal feedback, we don't get much. We get some effect size. So yes, it's a good thing to give your students feedback. Okay, they do benefit from it, but the effect size that is the greatest is when you start to give them what's called strong formative assessment. That is information, not only whether they're right or wrong, but the nature of the correct answer and some things or exercises they can do to clarify whatever it is that they're doing wrong. So this is just a way of indicating that assessment can be a very powerful tool in our quiver with respect to improving student learning. The challenge is actually developing good formative assessment tools and practices and then implementing them in classrooms. And maybe at the end of this talk, we'll talk about how technology can help you do that, because quite frankly, it's very difficult to implement some of the things we'd like to do without the assistance of technology. Okay, so enough of the where, what, and why, and a little bit about formative assessment. Let me sort of try to talk about some issues of theory. And this is based on an NRC committee that I chaired that was tasked with the job of sort of trying to figure out what do we know about assessment now that might, or what do we know from research in terms of cognitive psychology on learning, and what do we know from advances in measurement that would allow us to think about the science and design of educational assessment. And so we wrote this report called Knowing What Students Know. It was published in 2001. And the major point of the report is that we can never really know what students know. Okay? That in essence, what we don't have, unlike the physical sciences, we don't have measuring sticks that we can use. So I don't have the equivalent of a dipstick that I could just put in one ear and pull it out and say, Jones, up a quart. We just can't do that. So assessment, really, we have to think about assessment as a process of reasoning from evidence. What we're trying to do is to make inferences about what a student knows by engaging in a very principled process of reasoning from evidence. And the evidence is critical because the nature of that evidence will determine the inferences we're able to draw about what it is that students know. And one of my favorite jokes about this committee, this was a committee of about 16 distinguished scholars. We met for 2.5 years, and God knows how much the National Science Foundation paid the NRC to fund this committee. And the best thing we could come up with after 2.5 years was a triangle. But it's a very important triangle. We call it the assessment triangle. And it's trying to capture, I think, a critical idea about this reasoning from evidence process. And notice, down here at the bottom of this is this thing called cognition. It's basically arguing that our theories, our data, our beliefs about how students represent knowledge and develop competence in a domain is critical to the entire process. Because what we think is the nature of knowing and what it means to know then guides the design of the observations. Because in essence, the way what we're doing when we assess students is we're designing tasks or situations where the students are asked to write something, say something, dance something, perform something. They are asked to do something. And the something we ask them to do are our observations. That's all we have access to, are the observations. Those observations are the product of what's going on in their head. And so the belief system we have about what it means to know and what's important to know and the nature of that knowing should guide the tasks or situations we put in front of students. And of course, we need a third part of this, which is we need a way to make sense of those observations. So the idea is that cognition, observation, and interpretation reflect a coordinated system. And all assessment, in some ways, is fundamentally a process of reasoning from evidence. Now, what happens many times is, and this happens to all of us as instructors, we may not be articulate about what this is in our mind. We have our own, maybe, theory of this, which causes us to write questions and then take the information from that in some way and put it back into some interpretation. And oftentimes that's a very impoverished assessment system. Okay? Many of the exams we use, I would not exactly say are detailed, deep representations of what it means to know in the domain. But the point is that assessment is a very important reasoning process, and if we want to do it well, we need to pay attention to all three of these elements, and they have to be coordinated. Okay? So the argument we made was that the scientific foundations of educational assessment rest on two things: advances in the science of thinking and learning, and advances in measurement and statistical modeling. Because advances in the sciences of thinking and learning, that's the cognition vertex. In many respects, what we know about how students learn, etc., that informs us about what observations are important to make. It tells us what kinds of things matter, or should matter. And then measurement and statistical modeling informs us of how to make sense of those observations relative to that underlying theory. So it turns out that in some sense, assessment is a very simple conceptual thing. It's reasoning from evidence, but it's very complicated in terms of putting these pieces together in an effective way, depending upon how we want to use the assessment. So for those of you who know about this, we know a lot about how people learn. And we know a lot about how people learn in certain subject matter areas, and it ranges from the elementary grades on up into post-secondary. And I'm just going to give you three quick generalizations from that, because I'm not going to dwell on that, but I just want to make clear some of what we know with respect to student performance. And it has to do with understanding now much more deeply about the nature of competence and expertise. Okay? And the difference between experts and novices. Okay? So our students are novices in our disciplinary domains, and we're experts. If we go into somebody else's domain, we're novices. Okay? Now, one of the differences about the development of competence and expertise is that what experts know is an organized body of knowledge. So I think one of the key points about expertise is that being an expert in something doesn't mean you just know a lot. It has to do with how that knowledge is organized and organized for use. And that knowledge and performance develops in communities that value certain forms of knowledge. Okay? So if you are a mathematician, you develop expertise in the community of mathematicians that value certain kinds of practices. If you're in sciences, it values other practices. If you're in English, it values other practices. If you're in history, so in essence, performance develops in communities that value certain forms of knowledge and activity, like modeling in science or design in engineering, and it's tuned. It's tuned to patterns of activity. And what happens is, as students develop competence and expertise, their performance increases in scope and precision. And there's no magic levers. Okay? There's no magic levers. You can't turn a novice into an expert. Okay, if any of you know the literature on expertise, the estimate is that for somebody to become an expert in any domain, whether it's an intellectual domain, or golf, or tennis, or chess, 10,000 hours. 10,000 hours of sustained practice with feedback. And you have some hope of becoming an expert in something. Okay? And that's a fairly standard estimate in work from Anders Ericsson and others. So one implication is that assessments have to be designed to capture the complexity of expertise and competence performance. And that ranges everything from mental processes to participation in forms of practice. One of the things that we have to recognize is that if we want students to develop competence and expertise in mathematics, they have to learn to behave and perform like mathematicians. And so they have to, we talk about this in the cognitive literature as moving from legitimate peripheral participation in a community to the center. Okay? So you learn by observing how others do it, and then you begin to model the practices until you embody those practices of mathematical argument or historical argument and building evidence or scientific practices. So that's one. Development. Not all persons learn in the same way or follow all the same paths. And one of the things we know is conceptual change is very hard sometimes. And in fact, conceptual change can be one of the most difficult things to overcome because students we all come to situations with certain misconceptions. There's a large literature about misconceptions regarding the physical world that demonstrate, how many of you ever seen the video from Harvard, what is it,
graduates on science questions.
On science, yeah. I'm blocking on the name of the video, but it's a video that is shot at Harvard graduation. And it interviews Harvard graduates and Harvard professors and asks them a very simple question. What causes the seasons? And you know what? Most of them don't know the correct answer. Okay? They invariably say it's the distance of the Earth from the sun. Okay? Which is not right. Not right. And there's a large literature that shows that students who have taken a calculus-based course in physics and passed it with an A, if you give them qualitative reasoning questions about force and motion, they behave like pre-Newtonian 6th graders. Okay? So what happens is their conceptions about force and motion don't make any connection with what's in the text, and they can tell you, oh, well, this is the way the world works, and this is the way the course works. And they'll give you the course answer, but they actually believe that the world works a different way. So overcoming some of these conceptual challenges requires, we first have to know what they are, and then we have to create conditions that allow. So there's a whole bunch of instruments out there called concept inventories that help get at this in various domains of science and engineering. Whoops. So one implication is that assessment should identify specific strategies, knowledge representations, and forms of activity with respect to the role that they play in these trajectories. And these trajectories are very predictable. Yeah, and if we know what's going to happen with young kids developing knowledge of arithmetic. What kind of a trajectory? We know what's going to happen with respect to their doing simple addition. Including they're going to go from things like if you ask them what's 3 plus 2, they're going to go 3, 2, 1, 2, 3, 4, 5. Okay? And then at some point they're going to transition from doing that to going essentially 3, 4, 5. That's count on. Okay? And then they're going to actually progress to something called min counting. If you give them 7 plus 3, or if you give them 3 plus 7, they're going to pick the bigger number and count up the smaller number. And then eventually, like all kids with enough practice, they're going to recall the fact from memory. They're not going to count anymore. Okay? Very predictable. If we know that, then we can make a judgment as to whether a child is in the right place on a trajectory and whether there's a problem or not. So this is a true example, and take your time with it because it illustrates the dilemma for teachers. When my son was in the first grade in California, came home one day and he had a sheet that on one side had all the basic addition facts and on the other side had all the basic subtraction facts. And on the side that had all the addition facts, he had them all right. And on the side that had all the subtraction facts, he had almost all of them wrong. And the teacher wrote on the paper, "Christopher needs to memorize his subtraction facts." I looked at the paper and I noticed something. I noticed that when he was wrong, every one of his answers was off by 1. And when he was right, it was always when it was takeaway 1. So I just asked him a simple question. Sat him down, calmed him down, you know, because he was in a panic. He was home with the sheet. He's like, oh, you know. So I said, "Christopher, what's 7 take away 3? He goes, 7, 6, 5. "Christopher, what's 4 take away 2? 4, 3. Okay? So what this told me was something that was very important. One, he knew what subtraction was, conceptually. Okay? He knew it was a process of decrementing or taking away. And he didn't know his subtraction facts, but he had a procedure. And he had what we call a buggy procedure. Okay? Now, why did he get all the other ones that just were take away 1 right? Because he was also smart enough to know that 7 take away 1 couldn't be 7. Okay? So it told me I don't have a big problem here with him about subtraction. What I have to do is fix his bug. Okay? So it was really simple. I said, "Christopher, when you say that first number, don't put up that first finger." And I had him practice that and practice that until he went on his merry way, knowing now he could get all the answers right. And I knew that because he was going to do that, eventually he'd know his subtraction facts. Okay? That was a case of a diagnostic assessment. It turns out that the actual assessment the teacher gave was potentially diagnostic if she had understood what pattern of the results across the items might mean relative to what he was thinking and doing. Okay? And I swear, this is a true story. It did happen. So, about knowledge, disciplinary knowledge is organized in particular ways that facilitate its use. What experts have done is organize bodies of knowledge, not just in an arbitrary way, but in ways that facilitate their being able to use it. Okay? In fact, the knowledge that experts have is tuned to use. It's tuned to help them do their work. And it's developed in communities that foster identity and interest. I think this is another and very important part of the socio-cultural aspect of our understanding of learning and knowing. That learning and knowing is not a solitary act. It is a social act. It occurs in social contexts. And so this has all sorts of implications for what we assess and how we assess. Facts, procedures, etc., and practices. So one of the things what this tells us is models of the development of domain knowledge are critical because they tell us what are the important aspects of knowledge that we should be assessing. They give us clues as to how that knowledge can be assessed, and they can lead to assessments that are more instructionally useful, diagnostic and prescriptive, and they can guide the development of systems. So where do you look for these models? Well, you find some of them in the literature. I know that I've worked on stuff in engineering education where there's a body of knowledge about certain aspects of engineering. There's bodies of knowledge about physics, about chemistry, about history, about various disciplines. It is not a complete knowledge base, but it is very useful in helping us think about our pedagogy and our assessment. Okay, so enough of the theory stuff. Okay? Let's get down to the practical side of this. design. And it turns out that I want to make an analogy here. So our theories and knowledge, and empirical knowledge about learning and knowing is somewhat like the disciplinary knowledge in physics. And designing assessments is like an engineering process. So in engineering, when we build a bridge or build anything, the underpinnings are physics, the laws of physics. But engineers don't directly use physics. They use principles of design in engineering to build something for a particular context of use. So in terms of assessment, we have to think about assessment as a design process, a way of translating from theory into practice using a set of principled mechanisms and processes. So it turns out that assessment design spaces are very, very complicated, multiple dimensions. Okay? It includes what kind of knowledge, what's the time period over which the knowledge is being acquired or developed, what am I going to do with the information? Do I have theories and empirical data that are going to inform me? And how close or far is the assessment from instruction and the assessment purpose? So what's happened in the last decade or more is we have come up with principled processes that can help structure going from theory, data, or speculation to an operational assessment. And it's called evidence-centered design. And I'm going to illustrate that for you. And I'm going to walk you through it, and then I'm going to have you do an exercise that sort of gets you thinking in these ways. Evidence-centered design is really asking this question: what evidence do I need to have that would convince me or convince somebody else that the student knows things in the way in which I want them to? What's the evidence that is going to convince me that they have that competence? And then the issue is, what task or situation do I have to engineer that will give me that evidence? But we don't think about the task first, we think about the evidence. Okay? And the evidence relative to what? Now I'm going to illustrate this for you essentially by walking you through stages in assessment development that ultimately, notice at the end of this, you essentially have some assessment that you're implementing and delivering and you're scoring. But we're not going to start there. In fact, we're going to be far away from it. We're going to start up here by first asking the question of essentially, for whatever domain we're interested in. So in my case, I teach an undergraduate course in cognition and memory. What's important for students to know about cognition and memory? What are the important ideas? What's central to this domain? What knowledge and skills are central? What do I want students to know? I'm going to unpack that. And then I'm going to build a conceptual assessment framework using this evidence-centered process, a domain model. And I'll just illustrate it real quick and then we'll come back to it. Evidence-centered design has these three components: claims, evidence, and tasks. The claims are about the student. So in my case, my class, the question for me is, what claims do I want to be able to make about my students at the end of that class with respect to what I want them to know and be able to do? Then the issue is, what evidence would support those claims? How can I convince you that my students have that competence? What's the important forms of evidence? And then the issue is, how do I get that evidence? Do I give them a multiple choice test? Do I give them essays? Do I have them do a portfolio? How do I get the evidence? But I don't start by asking the question about the task first. I ask about the claim I want to make, or the claims I want to make, and the evidence. And then, really important, what features of the evidence are important and which ones are irrelevant. Okay, we'll work through an example of that. And the example I'm going to work you through is essentially, I had two examples. I'll never get to the second one. I'm going to walk you through what has been going on for the last 7 years, 8 years, in redesigning AP science courses and exams. How many of you know about the redesign of the AP science courses? No. This is the disjunct between higher ed and K-12. Okay, well, in case you didn't know, all of the AP science courses have been redesigned, and the AP science exams have been redesigned. And I'll give you the reason why. But it's not just AP science, biology, chemistry, and physics. This is happening in every AP course. Okay? And they're all following a similar process that we started in 2006. And let me sort of walk you through this and talk about, give you a synopsis of what this process was like and how it relates to these issues of assessment. I think many of you know, how many of you have had children that have taken AP exams? Okay. So if you've had students who've taken AP exams, you know that essentially they take a course and they cram for an exam and they pray to God that they score a 4 or higher on the exam so that some university can give them credit for having taken that course. Okay? And the AP process has been largely to mimic the freshman course. And the way in which they have built their courses and their exams, actually, is to go through syllabi of freshman courses like in biology and chemistry, look at the list of topics, say, oh, here's the common topics, and then they usually have faculty write questions on those topics. So what's wrong with that? Well, in 2002, the National Research Council wrote a report, which was a scathing report about advanced study of math and science in the U.S. And that was not just applied to the AP program, but the International Baccalaureate. Okay? And the problem was that, in essence, the courses in the exams did not emphasize, they basically said, we have to change what we're doing because what we need to emphasize is deep understanding rather than comprehensive coverage, like we do in many of our freshman courses, right? That is, we had the mile-wide, inch-deep curriculum problem. It didn't reflect current understanding of how students learn in a discipline, it didn't reflect current research directions, and it didn't emphasize inquiry and reasoning skills in science, which is really what science is about. It's not just about the facts. And one of the reasons, these are some data that are now a few years old, but it illustrates that for biology, chemistry, environmental science, and physics, if we add that up, and now it's even more than that, over 500,000 students a year are taking AP exams. Okay? And the issue is, what are they really learning about science relative to what we want them to learn? So that led to the National Science Foundation funding a project with the College Board, and I was the privilege to be the co-PI, or the PI on the project, in which the question was, how do we reframe AP Science? And so the conceptual framework for the AP redesign was really to start by asking, not what do we want to test, but what do we want students to know? So we started by trying to identify the enduring understandings and apply what's called backward design. Essentially, backwards design, Wiggins and McTeague have written about this in their book called Understanding by Design. It is a great book to think about how you structure and think about developing a course. It asks the question of, what are the really important things that I want students to know, and then you work backwards from that in terms of how you structure everything to make that happen. We use a variety of techniques, essentially, that would allow domain experts to to answer the question of what's really important in this domain of biology and what do we want students to know so we can get to a curriculum framework and an exam. And we used evidence-centered design. And I'm going to walk you through a quick version of that to illustrate what it takes to do this, because we're going to engage in a mini exercise to get you started on that with respect to thinking about your own domain. So we build upon the work of Wiggins and McTeague, how people learn, knowing what students know, and evidence-centered design. Now, just to give you an idea of how long it takes to turn something like this around, we started this in 2006. So NSF funded this in 2006. Here's the components of the process and the timeline. The first new AP Science exam was administered in biology last May. The new chemistry exam is being administered this May. The new physics exam next May. So this is a way of saying this is not, particularly for a high-stakes program like this is not a simple, slow thing to do. Although at the level where we have control of our own curriculum, it can be compressed considerably in time. And it has multiple components. So the first thing that we had to do was to apply this process of backwards design and evidence-centered design. And we start by unpacking the domain. Okay? That is identifying and elaborating critical elements of integrated knowledge. And what do I mean by unpacking the domain? It's not the same as saying, well, okay, what's everything in physics? It's asking, what is it in physics that fits this course? What do we want an AP student to know, or a freshman to know in the first course in physics, or whatever? So it's not all of the discipline. It is essentially something that's circumscribed to a particular course. And we used a multi-part framework for the domain analysis that looks something like this. The idea is that we start out with big ideas, and we tell the disciplinary folks, okay, you've got from 4 to 7 big ideas. Okay? No more than that. Okay? So it basically says, if you are a biologist, what are the really big ideas in biology that organize and drive your discipline? And related to those are what we call the enduring understandings that are connected to those. That is what we want students to master. And then we have a third level, which are elaborating details. And oh, by the way, there are these processes of reasoning in the domain. So we have this this 4-part framework, which is both, you might sort of say, the content side and the reasoning side. So the content side ends up, and I'll give you an illustration, a concrete one in biology in a minute, that the idea is you have a framework which sort of looks like a concept net, but it's much more elaborated than that. We have some big idea, you have enduring understandings that are connected to that big idea, and then you have supporting understandings or details that flesh out that model of the domain. And it is done graphically, but it's also done in a narrative. Of course, you don't do this arbitrarily. You have peer review. This is how it felt. And it turns out that the domain experts were very good over time at being able to try to articulate the big ideas, the enduring understandings. They were not so good at developing the reasoning part. So we had to help them. And in AP Science, we laid out a set of what we call reasoning practices that basically could be applicable in all of the sciences. I'm not going to go through the details of this, but if you look at that list, it basically says, look, it's not just knowing the stuff in the content side, it's also being able to reason with that in particular ways and putting those two things together. And so laid out a set of practices at multiple levels, including unpacking the first level to a second level, and the second level to essentially what kind of evidence would support that. So let me give you just a quick example. So if one of the practices is being able to work with scientific explanations and theories, and embedded underneath that is to be able to justify claims with evidence, then we have to say, well, what kind of observable data would be needed to support that claim? And then you get examples of this, which sort of says, well, the robustness, the appropriateness, etc. Now, these are general characterizations. And so what we ended up with was what's called a domain analysis. You got two pieces of the domain analysis. This is the content. These are the practices of scientific reasoning. And we now have to essentially go the next step and essentially develop the assessment argument. Because now we have to put this together and apply this evidence-centered design process so we can build a framework for what we want to assess. And it was done by essentially asking these questions. What's the claim we want to make about students with respect to the knowledge and the practices? What evidence would we accept? And then we get to designing a test or tasks. So, so the way in which this was done in AP Science was to say, let's put the content and the reasoning together to establish claims and evidence. I'm going to give you a quick illustration, and then I'm going to show you what biology looks like to fill this out, so we'll have time for you to engage in the exercise I want you to. So if we think about this in terms of a big idea, an enduring understanding, and a supporting understanding, and a science reasoning practice, then what we're going to do is we're going to lay out a claim. The student is, we're going to lay out the evidence, and in this case we're going to lay out what level of achievement we think that is on an AP test. So here's an example from chemistry. Chemistry, big idea. Chemical and physical properties can be explained by the structure and arrangement of atoms, ions, or molecules, and the forces between them. The enduring understanding has to do with electrostatic forces of attraction that hold atoms together in a unit called bonds, and then covalent bonding. And then the skill was the student can justify claims with evidence. So this translates into now, this is what we would like to be able to claim about a student in terms of what they know and they can do at the end of an AP course in chemistry. The student is able to use evidence to justify claims involving the classification of covalent bonds in terms of polarity and the relative strength of those covalent bonds. So it looks like this, and this is the evidence. Notice I haven't shown you an item yet. I haven't shown you a task, because you don't get to the task until you've sort of tried to articulate all of this information about the domain analysis, the domain model, the claims, and the evidence. But you do get there eventually. So you end up developing what we call a domain model with claims and evidence statements that then supports two things: a curriculum framework and an assessment framework. Now before this, with AP, there really was no curriculum framework. It was just a list of things that were on the exam. But now you're going to end up with a curriculum framework and an assessment framework. And I'll just illustrate a little bit of the curriculum framework, and then we'll talk about the assessment. So you should really go look at the AP Biology Curriculum Framework and the AP Chemistry Curriculum Framework. They've been available for a couple of years, and what they do is they lay out in a very explicit fashion what are the big ideas, what are the enduring understandings, what are the expectations about students with respect to these practices and these content. So here's the structure of AP Biology. Okay? Oops. Here's the structure of AP Biology. Biologists came up with 4 big ideas. Only 4 for the entire domain of biology. A set of enduring understandings connected to each, essential knowledge, science inquiry practices, and then you produce learning objectives. So here's the big ideas in biology. Process of evolution drives the diversity and unity of life. Biological systems utilize energy and molecular building blocks to grow, reproduce, and maintain homeostasis. Living systems retrieve, transmit, and respond to information essential to life processes, and biological systems interact, and these interactions possess complex properties. Now, if you read the elaborating information about that, it provides a lot richer description as to why that is a big idea in the domain of biology. And then for any big idea, like this first one, you have a set of enduring understandings. These are the things we want students to be able to understand and work with in a course on biology. Change in the genetic makeup of a population over time is what we mean by evolution. Organisms are linked by lines of descent. Life continues to evolve within a changing environment, and the origins of living systems is explained by natural processes. This is essentially the unpacking of the important ideas in biology we want students to be able to reason with. And so, by integrating the content and the practices, you end up with putting together content and practice, and you create a learning objective. Okay? The learning objective is now essentially the claim you want to make about a student who has successfully mastered this AP biology course. The student is able to evaluate evidence provided by a data set in conjunction with a phylogenetic tree or a simple cladogram to determine evolutionary history and speciation. You're almost to assessment. Yeah?
Question, you're saying this is what an AP student should know in biology, correct?
Mm-hmm.
Do you also agree that this is what a student in higher ed as a freshman should know in biology?
Well, it's a great question, because the determination of this was done by a combination of higher ed domain specialists and secondary biology teachers. And so the answer, I would say, is yes for populations of university instructors who have looked at and worked in the context of the AP course. In fact, one of the things that was done was to run a lot of these learning objectives by higher education faculty, as well as the items that have been developed. And you have the same thing in chemistry and in physics. So what has been created is a very detailed list of learning objectives that students would come out of a course. Now, you're asking another question, which is, to what extent has this actually been implemented in freshman biology? And that's another can of worms.
Which is required for gen ed versus the major. For major, yes, but for a gen ed person.
They would say this would be for a gen ed person. This is somebody who is taking a first course in biology.
Yes, sir, which doesn't exist at most universities. It just doesn't. I'm just telling you the truth. I mean, there's very few non-majors can take the major. And it's not like other disciplines, like say my colleague in sociology. No, I'm sorry, Barbara. Or in psychology, you can take those courses, but as a science major, most universities have separate courses for gen ed because it's just too much content. It's too much. But you just opened a can of worms. You're saying that a college freshman should be able to handle this.
Yeah, and in fact,
this is a lot of content.
One of the ways in which they have tested the items that were developed for the AP exam was by having university instructors administer them in their courses to their biology students and seeing how well their biology students can now do on the AP type questions.
Yes.
And the answer is not well. And in fact, we can go into a separate conversation about this, but biology instructors, when they looked at the questions that were derivative of this, said these would be really good questions for my course, but I couldn't ask this many of them because they're too challenging. So in some ways, there is this filtering process of content and topics versus what's really important for them to understand.
And then in all fairness to my other colleagues in other non-science, the biology majors would probably have problems with the physics and the chemistry also. I mean, also, to give credit, no, because biology or biology.
There's another interesting piece of this that I should mention that relates to higher ed. How many of you are familiar with the changes in the MCAT? You are, because you have to be. So the MCAT is the admissions test for medical school, and the MCAT 2015 is changed dramatically because it now requires students to know content but be able to reason with it. Coincidentally, I was involved in helping them make those changes. But there's also a new MCAT exam which has to do with the biological, psychological, and sociological foundations of behavior.
Right. Which might change.
And that's a completely new
Yes, sir.
exam.
Which may even change the whole forefront of pre-med in terms traditionally it's been biology majors, but now you're going to see psychology majors, sociology majors, they're going to major in that because of the problem. My hypothesis is that we have gotten to, our students have been able to learn how to test well. And that's why the ACT, I've heard through the grapevine that it's changing because the scores has been inflated. You know, the scores have, so it doesn't really reflect how well the students can really do in college. And back in my time, you only took the ACT once. And now you got kids taking it 3 or 4 times, plus you got Kaplan coming in. And that's what's happened to MCAT. MCAT has no longer been able to distinguish who can do it or not. And that's why they have to reinvent it.
Well, yeah, because MCAT was again, if you looked at the MCAT test, it was a lot of we might call content knowledge.
Yes, sir.
And not much in the way of reasoning with the content. Just a couple of things about impact on teachers, AP teachers. It gave them choice of examples. This way they didn't have to cover everything. So for an important idea about genetic disorders in the past, because they never knew what was going to be tested and how it was going to be tested, they had to cover every one of these cases, and rather than each case is an example of a particular important idea, and it's the idea that's being tested rather than what do you remember about Tay-Sachs or in other examples like that. It changed also the labs completely, changed them from essentially cookbook type things to essentially much more a scientific inquiry and reasoning process. A whole new set of labs were developed. And it changed the exam. It changed the exam in some very important ways. So in the new AP biology exam, and this will be true of chemistry and physics, there's no test items that focus on low-level cognitive recall of just facts. Items now require students to produce evidence or engage with the evidence, even in multiple choice type questions. One of the consequences was the exam was reduced in terms of multiple choice and more in the way of constructed response and extended constructed response. Here's an example of a multiple choice question. So the point is, you can write good multiple choice questions that get at deeper understanding. It's not easy to do, but you have to have a target in mind. And in this case, the idea is they have to choose something that both predicts and explains what the mechanism is. It produced a new kind of item, which was a grid-in, so that students couldn't just sort of pick a number and try to work backwards from it. They actually had to be able to do the calculations and be able to understand how to do it. Here's a sample grid-in question. Again, they found new ways to still use paper and pencil bubble-type items, but to require different levels of cognitive demand. And then they added short free response questions like this, where they give them some data, some evidence, and ask them to construct an argument and an explanation. Okay? Now, again, remember, this took time to get to this stage. We started this process in 2006, and for something like AP, AP Biology didn't get actually, the new exam didn't get implemented until 2013. Chemistry 14, 15. It doesn't say we have to take that long, but when you have a high-stakes program like this, you've got that issue. Some of the impact, okay? Now this is an interesting one. When you use the big ideas to frame your exam, it changes what's on the exam. So in 2008, 12% of the questions had something to do with evolution. In this new exam, 35% did. Okay, reflecting the importance of that in the domain. There were new kinds of questions, and because of the use of evidence, the number of multiple choice questions was reduced. And this is a really important thing about designing an exam. Because the exam was tied to an explicit model of what evidence we wanted, they could rely on fewer multiple choice items and have the items be linked to specific claims they wanted to be able to make about student competence that came from the multiple choice and from the constructed response. It was a much more principled process. So what did it do? It's changed the way about 10,000 to 12,000 high school biology teachers are now teaching AP biology. And it's not been an easy change for a lot of them. They've had to replace labs. In many cases, they've actually had to incorporate mathematical skills. And this past May, 180,000 students took the new exam. And interestingly enough, the distribution of scores on that exam, 1, 2, 3, 4, and 5, changed. There were far fewer 5s and 4s than has historically been the case. Not surprising. Many kids were not ready to be able to perform at that level.
Well, I would debate that in order for a student to do well on something like that, number one, they have to have the interest. Second, they have to have the ability. And third, the motivation. So a kid, a student really does not have that, or they've just been told, I should go on, no, they go through the progression of science, because they've done well, but they're not really, to get to that point.
Well, typically with
some college professors would have problems, with some of these test questions.
Well, they would, but typically kids taking the AP exam are motivated to do well on them because it has consequences.
There's different types of motivation. They're doing external. I want internal motivation.
Well, we all want it. We all want intrinsic motivation. Yeah.
So you said there were 63 multiple choice questions?
I think it's 63.
It seems like you probably have many more learning objectives than 63. How do the questions and the learning objectives connect?
Okay, good. It's a great question. Essentially, the questions are associated with particular learning objectives, and it's not a one-to-one match. So there are some questions that actually are aligned with multiple learning objectives, and that because of the way in which they're structured. So yes, there are more than, if you actually look at the AP curriculum, there's lots of learning objectives that are listed, and then the exam samples a substantial part of them, trying to match the big ideas as well as the practices and where they come together in the learning objectives.
So it misses learning objectives as well?
Excuse me?
Like does it not cover certain learning objectives?
Yeah, it has to not cover it, because if it was going to cover all of them, it would probably be too long. On the other hand, it covers the learning objectives in a very principled way with respect to the distribution aligned with big ideas and the distribution associated with practices. It's very interesting. If you're interested more in the exam, you can go to the College Board AP website, and they'll give you the questions from this. At least they'll give you the constructed response questions from this year. They'll give you the scoring guides, and they'll give you examples of student work that met particular criteria. They're very transparent about trying to put this stuff out there in terms of what they're demanding. So what's some lessons that we learned from doing this? No pain, no gain. This is very hard work to do. It is challenging. Trying to do this process of backwards design and evidence-centered design it's challenging to execute and sustain. In order to do this, you really need to have multidisciplinary teams. And you need to have them come together and engage in a sustained process, and a lot of this is negotiation. I saw big ideas, it's like Survivor, voted off the island. Debates among disciplinary experts about, is that really important or not? One of the things that was most fascinating as a non-disciplinary expert participating in this, because I'm a psychologist and these guys were talking about biology and chemistry and physics, one of the roles I could play, and this is where psychologists are really helpful to others of you, is they can ask what I would call, we're good at doing non-directive therapy, which is tell me more, explain that to me in a way that makes sense to a normal human being. Okay? And that's a hard process to do, because what it's asking experts to do is to make explicit what is implicit and tacit in their knowledge structures. And that is a challenging thing to do. It is kind of like knowledge engineering. And it does. It requires time, money, and patience, but there's a big value added from this. Yeah?
I'm just curious, early in your presentation, you mentioned the importance of the formative assessment piece. Here you're talking about a summative
Yes, right.
assessment, obviously. Was there a formative assessment process incorporated in the retraining of teachers or in the development of your assessments?
Yes. It's a great question, a really important one. So we started with the target of the framework and the assessment framework, which would lead to the high-stakes exam, but it also led to the production of a set of formative assessment tools and resources and other things for teachers to help them structure a curriculum and instruction process that would prepare their students to be able to do what's demanded on the high-stakes exam. So yes, they've been working on the formative assessment components as well, although that trailed the summative, because in some respects they had to develop that full assessment framework, and then because the College Board, at least until Coleman came in, is not a curriculum group, they don't want to produce curriculum. On the other hand, they are committed to supporting their teachers in implementing the kinds of instructional practices and materials that are going to help students learn in the way that's intended. So they have got formative assessment tools and tasks and scoring guides and things like that.
And that's on the website along.
You'll find some of that there. Some of it is still under development, but it's part of their ongoing process with respect to revamping all of these courses in terms of providing resources to the teaching population. So we haven't talked about the V word in assessment, but validity. But validity is the holy grail of assessment, because validity is essentially the evidence that you are assessing what it is that you're claiming to assess. Okay, that you're measuring the construct and the knowledge that you're really intending. And so the idea is that by engaging in this systematic front-end design process, you're building a validity argument on the front end. You don't have to wait till the back end and sort of say, well, here's my exam, what does it correlate with? What else can I use to sort of structure an argument? I mean, for example, one of the problems with things like the ACT and the SAT is their validity arguments have nothing to do with how they're structured. It has to do with the fact that they predict something else. So much of their validity, in fact, that's one of the arguments about why you're seeing change in those things. So there's a variety of implications for science teachers and students, but I'm realizing because of time, I want to get to the exercise that I want you to do, which is essentially, we'll use the time remaining to start a process in which what I want you to do is to get together in small groups. Maybe you want to do it in common disciplines, so you can have talk to each other, or maybe you want to do it in mixed. And essentially, pick a course or a part of a course that is a core part of the curriculum, and try to begin this process of specifying elements of a domain analysis of the course. So if somebody said, you must be a psychologist.
No, I'm a sociologist.
You're a sociologist, okay. I wouldn't want to offend you by calling you a psychologist. Even though that's what I am. But I recognize our disciplinary differences. So, yes, we're good at that in the academy. So the question is essentially, in a key course in sociology, okay, how would you begin to frame or begin to elaborate? What are 2 to 5 really key ideas that are really important in that course that relate to what you want students to know and be able to do? And this is just an exercise in part of a process that I'm hoping you'll take away from here, which is to go from trying to do the domain analysis to something akin to a domain model, to starting to think through what you've got in place, including the assessment. So I said, let's take 20 minutes, get some coffee, get something else, set up in small groups, and just start having the conversation about what this might begin to look like if you did something like we tried to do with the AP courses. And I should tell you, this isn't just work in science. The same thing has happened with the history courses, the language courses, all the other. So AP is redesigning all of its courses using exactly the same backwards design, evidence-centered design logic. So let's reassemble about 20 after, and then we'll sort of see how painful this was for folks.